transport diluted, but in reality, I use the two.
Great, Mehdi. Well, thank you very much. There are more questions waiting for you in the chat. I think that people like the presentation, and yes. So I thank you very much, Mehdi. So I'm asking people maybe to write in the chat where you are going. You know, are you happy? You know, is and so on and so forth, right? But to welcome Donal Finegan, so Dr. Donal Finegan from NRL. So it's a big pleasure for us, Donal, hosting you here today, and welcome to this webinar series. Many thanks for having accepted the invitation, and well, we are very much looking forward your lecture today.
Okay, and thanks, Alejandro, for inviting me to this webinar series. My name is Donal Finegan. I work at the National Renewable Energy Lab, and I'm going to talk about how we've embarked on a project to understand the limitations of fast charging and then to manufacture electrodes that are capable of fast charging. So just a bit about NREL first. NREL is one of the U.S. Department of Energy's national labs. We're based at just outside Denver in the foothills in Colorado. The lab employs about 2,500 people. We've worked kind of equally with universities and industry to ensure that the technology can have an impact on the market. And our campus operates as a living laboratory. So not only are experiments done in the lab, but often the labs themselves and the buildings are experiments too, like building sciences, for example, and novel transportation methods, including this autonomous shuttle we have going around campus that it kind of fulfills the purpose, but also providing data for other engineers around NREL to do their own research on autonomous vehicles. So there are 4 main departments within NREL, focusing on renewable power, sustainable transportation, energy efficiency, and energy systems integration. And so very much the lab covers from the fundamental sciences and chemistry all the way up to modeling and predicting grid needs as we transition to new energy technologies and to new modes of transport, there are substantial challenges in the large scale as well. I primarily work in the vehicle technologies under the sustainable transportation umbrella. So all of my research pretty much is focused on enabling electric vehicles through improving the performance and safety of lithium-ion batteries. So fast charging is one of those challenges that's facing lithium-ion batteries, and as a good first step towards trying to resolve the problem of limitations of fast charging, it's understanding the problem is critical. So these are the 4 most important factors for the success of electric vehicles. There's cost, range, lifetime, and the ability of the vehicle to fast charge. These are roughly in order of importance. So cost is most important for people who afford the cars, range to be competitive with a combustion engine, about 300 miles, a lifetime that's about 200,000 miles or so of the vehicle that it can last that long, and then the ability to fast charge in a time that's almost competitive with refueling the combustion engine. So we're kind of thinking about 10 minutes, to about 80% charge is a target metric of the Department of Energy. Fast charging is also important in a few ways for the success of adoption of electric vehicles. Firstly, some people have range anxiety. So if you're doing a long road trip across Europe or across the US, you want to be able to stop and charge a vehicle in a reasonable amount of time. So instead of waiting 8 hours at a charging station, for example, to charge the vehicle, ideally you would be able to do it in about 15 minutes to 30 minutes to get another 300 miles on your road trip. Fast charging is also an equity issue as well. So, for example, lots of neighborhoods in big cities, for example, affordable housing neighborhoods, may not be equipped with the expensive technology to charge their vehicles at their home, right? Which is kind of a luxury, I'd say, of folks that can afford to install fast charging stations in their home or just charging stations in their home. to charge their cars overnight. Some apartment blocks simply just don't have this. So what if somebody's living in an apartment block and cannot charge their car overnight and needs to charge their car on the way to work in the morning? This is where fast charging becomes very important. So to be able to alleviate the strain of somebody that doesn't have a charging station at their home, to have to drive somewhere else and not have to wait for 8 hours, but rather they can charge every morning on their way to work. So fast charging is a very important equity issue to solve as well for certain neighborhoods. So these are 4 main challenges. Cost is largely under control. The Department of Energy target cost is about $100 per kilowatt hour. That's considered to achieve about cost parity with the internal combustion engine. And I've heard that some companies are at that point or approaching that point. Many of the large manufacturers, I understand, are approaching that. So this is kind of an industry challenge of cost. It is going in the right direction. Range, lifetime, and fast charging are a trilemma. You can pick 2, but generally the third is sacrificed. And because of range and lifetime are the most important, fast charging is the one that has least priority currently. And that's where we are working. So we can achieve high energy density cells for range. They can last for thousands of cycles without significant degradation, but they cannot charge fast. Now, if you do charge them fast, then this will affect lifetime and range, because there's an issue with more rapid degradation associated with fast charging that I'll go into. So this we want to understand firstly the cause of limitations of fast charging, and we've got research at UNREL that bridges multiple length scales from millimeters to nanometers. But in this talk, I'm just going to focus on the electrode scale and talk about the limitations at the electrode scale. So in a lithium-ion battery, the main limiting factor is on the graphite electrode. So during charging, we delithiate the metal oxide cathode and lithiate the graphite anode. And unfortunately, graphite has its potential versus lithium is about 1 volt when it's in a pure graphite form. And this means that we only have a luxury of about 1 volt over potential to apply to lithiate the graphite before the potential versus lithium on the graphite side decreases to below 0. Now, overpotential is very important to induce fast charging, and so this is a major limitation in that if we go below 0 volts and apply more than 1 volt of overpotential, it becomes favorable for lithium to just plate on top of the graphite instead of inserting itself into the graphite. And lithium plating is a concern for a few reasons. It's a safety concern. It's very unstable metal. It reacts very readily with the electrolyte. And also if lithium plates and starts to react with the electrolyte, it very rapidly decreases the capacity of the cell. So a lot of those reactions are irreversible, and this leads to lithium consumption. And so that lithium can no longer be used for charge and discharge. And transport limitations, as you can see in this figure, are a major concern. So as Mehdi covered in his last talk, these lithiation gradients can occur even at very low C rates, but we're talking about full charging in about 10 minutes, so that's about 6 C. So the lithiation gradients can become extremely severe. And with those lithiation gradients, the local potential versus lithium and some regions, particularly near a separator, can very quickly go below 0 volts and cause lithium plating. So lithiation gradients are a big concern. And we wanted to understand the lithiation gradients and also the behavior of graphite within thick electrodes, so high energy density electrodes that are favorable for range in the electric vehicle. And we designed this experiment where we made a coin cell with a small electrode pucks of about 4 millimeters in diameter. These electrodes were they were thick electrodes, about 100 to 110 micrometers thick. So they were high energy density electrodes. And we designed this cell such that it was favorable for high resolution X-ray diffraction, high speed and high resolution X-ray diffraction. This work was conducted at the ESRF in ID15A. And we used a beam size that was about less than a micrometer in spot size, and we conducted step measurements of XRD from copper current collector to the aluminium current collector, so through both electrodes, with a step size of about 3 micrometers. So stepping down, as you can see on these yellow dots, from current collector to current collector. And in this talk, I'm not going to cover the NMC electrode, but I'm just going to cover the graphite. And the graphite electrode, with the speed of measurement at 100 XRD measurements per second, we captured the full depth of the graphite electrode in about half a second. So with about 3 micrometer resolution. So we were able to see the composition of graphite, the lithiation state of graphite with a resolution of 3 micrometers, captured in about half a second. So very good time, spatial and temporal resolution. And this is the raw data. So you can see this is the line profile. I should explain X-ray diffraction. We get peaks from certain crystallographic phases. Graphite, LIC12 or stage 2 and LIC6 have very distinct crystal peaks, diffraction peaks, and you can see them moving over and back as the electrode lithiates and delithiates here. And you can see the y-axis is depth. So up here is the graphite. You see the graphite peaks shifting over and back. And here is there's a lot of NMC peaks, but I'm not going to talk about those. I'm just going to focus on this data that we collected on the graphite as a function of depth. And you can already see that there's, at any point in time, often there's existence of 3 phases. So some areas close to the separator that you can see the LIC6 peak, LIC12, and graphite. So you can already see from the data that there's going to be very severe lithiation gradients in this cell. And when we conducted Rietveld refinement on this data, we were able to estimate the lithiation state, X and LAXC6, as a function of depth and time. So on this axis, we've got depth. 0 is close to the separator, 100 is close to the current collector, and then over time. And you can see at all times there's a severe lithiation gradient, but in particular at the beginning. Severe lithiation gradients where there's high lithiation close to the separator, low lithiation close to the current collector. And we can play this in real time. So this is the current. We achieved 6C actually for about 40 seconds or so, and then it went to constant voltage. These are thick electrodes, so the 6C constant current we didn't expect to last beyond about 40 seconds because of the overpotential needed to drive that current. And you can see the evolution generally of the X and LAX, which is in blue here. The state of lithiation is growing. The current goes constant current and constant voltage. And then down here, you can see the contribution of the individual stages. So we've got LIC6, stage 1, LIC12, stage 2. With this experiment, we weren't able to decouple the resolution of the other stages, stage 3 and 4. So we bundled them into kind of one stage, so 3, 4. That's about LIC30 or LIC18. And you can see the mass fractions of those phases as a function of depth and time here. So you can see close to the separator, to about 40 micrometers in depth, we get a lot of stage 1, so full lithiation, whereas the rest of the electrode, there's very little stage 1, and most of the electrode consists of stage 3 or stage 2. So you can already see very severe lithiation gradients in this electrode. And this data was plotted here on a static plot. It's a bit easier to look at. And on the y-axis here is the state of lithiation, X and LAXC6, and the x-axis is time. And the points are color-coded as a function of depth. So 0, again, is close to the current collector here. That's current in blue. And as it approaches, close to the separator. And as it approaches the current collector, it goes to purple. So you can see that the areas close to the separator pull away very quickly in state of lithiation, while regions close to the current collector don't respond at all for the first couple of minutes, or first minute or so. And so this shows the extent of lithiation gradient. And then over time, the region of the current collector starts to lithiate to a certain point, and the region close to the separator starts to slow down in lithiation as well. Now, because we conducted Rietveld refinement, we were able to look at the contribution of the individual stages to this overall lithiation state as a function of depth. And so we can see the response of graphite as it transitions from graphite to stage 3, to stage 2, or LSC12 to stage 1. And there are energy barriers associated with this crystal structure's change in the graphite. The biggest energy barrier is the transition from stage 2 to stage 1. So the highest overpotential for lithiation is needed to make that transition happen from stage 2 to stage 1. And this has consequences that I won't go into in great detail in this talk, but they're covered in this paper on the behavior of graphite and the influence of energy barriers, Gibbs free energy barriers to phase transitions. So we can see, firstly, that we see at the surface, we see very rapid growth. So in blue here, rapid growth of stage 3, also rapid growth of stage 2 in blue, and then the blue starts to decrease. So the surface has a high concentration of stage 3 and 2, but then starts to decrease, and that decrease is associated or correlated with an increase in stage 1. So it transitions to stage 1. But you can see that only really the top 40 micrometers or so actually reaches any fraction of stage 1. Most of the electrode doesn't reach it at all. And so this will have consequences for lithium plating as well. So as you reach stage 1, that means we can no longer lithiate beyond that point. So the local overpotential to drive current will spike up, is expected to spike up around the surface areas, around the separator. And that overpotential is very likely to exceed the 0 volts that I mentioned before and end up having favorable conditions, local conditions for lithium plating. And so with X-ray diffraction, we are also able to detect plating. So on the y-axis is depth, here on the x-axis is time. The color now is lithium weight percent, so it's a pure lithium metal. And so we can see the growth of lithium metal close to the separator, which correlates roughly the depths of high concentration of stage 1, down to about 20 micrometers. And then we also actually see that when we reach constant voltage stage, go to low current, some of that lithium plating is reversible. So we see that a decrease in the lithium weight percent after a certain amount of time. Some of the lithium plating is irreversible, and we talk about that in the paper as well. So that at some point, the magnitude of lithium plating becomes irreversible, and you end up with major capacity loss that can never be retrieved in that cell again. The same transport limitations and lithiation gradients are observed during discharge. So this was a 6C discharge. You see very rapid reduction in state of charge close to the surface, very little response until about 400 seconds close to the current collector. And then surprisingly, we see that everywhere except the very vicinity of the surface fully delithiates. But the surface regions close to the separator don't fully delithiate despite the current being drawn. And we can get some insight into what's causing this. So we can see a reduction in stage 3 generally. We see kind of an increase and decrease of stage 2 that's caused by stage 1 transitioning to stage 2 initially, so we see an increase, and then stage 2 transitions to stage 3, so we then see a decrease. And we see that all of the lithiated state close to the separator is in the form of stage 1, and it only correlates with where we saw lithium plating. So we saw coexistence of LSC6, full lithiation where lithium plating is present, and we think that that's due to the lithium plating keeping the regions directly underneath in a full lithiated state, even upon discharge. So there are still questions around whether this lithiated state inside the graphite is ever recoverable, given that there's going to be a plate of lithium on the graphite, and if we can reverse that and retrieve that, then I'm still not sure about that. So in summary, the major limitations associated with fast charging are caused by lithiation gradients. This is the data superimposed onto a nano-CT image of graphite. And we also see that there are very severe current density gradients as well at certain periods of time. during fast charge and discharge. You can see a kind of short-lived red region there. And lithiation gradients are the biggest solution to resolve fast charging issues in thick electrodes. And so we can relieve lithiation gradients, with improving the ionic conductivity and transference of the electrolyte, decreasing the thickness of the electrode, which we don't really want to do, to make sure that because it affects energy density of the cell, or we can reduce the tortuosity of the electrode. Now, because we don't want to actually change the materials in the batteries, because performance is key. We need to maintain high energy density and long life. So the current electrolytes and electrode materials are very good at that. We want to look at how can we continue to use existing materials with electrodes, but make the electrodes charge faster without lithium plating. And one way to do that is to reduce the tortuosity and leave the lithium concentration gradient. So we'd like to go from this, where we've got a severe lithiation gradient, red close to the current collector, close to the separator, blue close to the current collector, to a less severe lithiation gradient inside the electrode. And we do this by introducing highways or channels, low tortuosity channels inside the electrode to facilitate lithium ions reaching deeper into the electrode at the earlier stages of the fast charging process. And this is an example, kind of taster of what's to come. This is an NMC electrode. We see the particles. This is 112 micrometers thick. We see that this is placed in the current collector at the bottom here. This fibrous material is just part of the sample preparation technique. So it's only the particles in the current collector that's important here. And this is before laser ablation, and then we use laser ablation to introduce these highways that I showed in this illustration to alleviate the lithium concentration gradients. So that's the goal. The first step of this process was to guide our synthesis manufacturing techniques with models. There are some systematic limitations of what we can achieve, and they're based on the laser conditions. So how big is the spot size of the laser will determine our minimal channel width. So if you let the model run unconstrained, the model will probably predict extremely small width channels with tiny pitches as well that are simply can't be achieved with actual laser technology. So we have to firstly characterize what the laser is capable of, and some of these parameters that are important to restrict the range of parameters that the model goes to include the width of the channel, the pitch of the channels, W2 and W1. Alpha is the angle of the channels. Can we control the thickness of the channels, so T here as well? And so through characterization, we were able to characterize the W2 for the laser system that we use will be limited to about 40 micrometers. So we constrain the model of a W2 of about 40 micrometers. The alpha is about 75 degrees. We constrain the model again to about 75 degrees. This work was conducted by my colleague, Francois Seglio-Beretta, DINREL. And then Francois conducted a very thorough parameter sweep based on those limitations. So Francois looked at what is the optimal channel depth with the system, with the systematic limitations that we mentioned, that can achieve high capacity during fast charging, a low plating intensity with very little theoretical capacity loss. So the capacity loss will come from because you have to remove some material to introduce these channels, and so we want to minimize that. We set that limit at about 10% maximum loss of material. And so Francois did this very thorough parameter sweep where on y-axis here we've got cathode channel depth, anode channel depth, and channel spacing, and looked at the interaction of those three parameters on normalized capacity, plating intensity, and theoretical capacity loss, and then cell voltage cutoff time. So that's the time that it takes to reach the time of the constant current step of the constant current, constant voltage charging. And Francois found that there's an optimal channel depth of about 70 micrometers in the anode and about 56 micrometers in the cathode. So the two electrodes don't contribute equally, right, to fast charging. The anode is the most important, and it needs the biggest improvement in transport. And the cathode is not as much of an influence on the fast charging process, so it doesn't have to be laser bladed as much. And so Francois' models were predicting the major benefits from introducing these features. So in this graph, for example, we've got percent of theoretical capacity. You can see at low C rates in the x-axis, we have less capacity because we have removed material. But as we go to higher C rates, like a C rate of about 1.6 or so, we start to see benefits of the laser ablation channels. And in particular, we're looking at 6C, that's where our interests are, charging in 10 minutes. We see about a 25% increase in the theoretical capacity that can be achieved in a 6C constant current, constant voltage for 15 minutes charge protocol. And we see, we also see benefits in the cell voltage cutoff time, and we see major benefits in the reduction in lithium plating. And so this is a plating intensity. We go from plating intensity of about 1.7 down to less than 0.2 for a 6C rate. So the next question then was, how can we actually achieve those channels dimensions that Francois predicted? So we did extensive laser ablation optimization, understanding the relationship between laser parameters like power applied to a certain area, pulse rate, wobble, on the microstructure, and the influence of these parameters on the microstructure of the electrodes. And so here, for example, is a simple graph of laser power in watts and the trench width that we can observe from these images. And as you'd expect, increase the power, you'll increase the depth and trench width of the laser bladed process. And then the question was, can we control the depth to the extent that we can achieve the 50 micrometers depth on the cathode and 70 micrometers depth on the anode? And we found suitable power and operating conditions that we could achieve that. And so here's an example of how we aimed for about a 50% channel depth, 90%, 100%. We were able to control that fairly well on the shape and size and depth of the features. And these are images of the electrodes that we settled on for actual electrochemical characterization. So we can see, this is a photograph. You can see the channels going from top to bottom here. These two areas of circular removed material are for welding onto the coin cell current collector. With 6C, we need very good electrical contact to the current collectors we weld. And these are the channels on the NMC and the graphite. So for electrochemical evaluation, this was a protocol. We conducted a formation process. We did then initial C/2 cycles to measure the total cell capacity. And then every 50 cycles, we repeated that C/2 cycle to quantify the capacity fade. And the fast charging conditions were 6C constant current of 4.2 volts, followed by constant voltage until a total of 10 minutes, followed by 15 minutes of open circuit, followed by 0.5C constant current discharge to 3 volts, followed by constant voltage to C/10, and then a 15-minute open circuit again after that. And each cycle took approximately 1 hour. So obviously the 0.5C discharge, it doesn't reach the full capacity, otherwise that would take 2 hours because the 6C in 10 minutes doesn't reach the full capacity to discharge. And here are some of the results. So here on the y-axis, specific capacity, milliamp hours per gram of the NMC. On the x-axis, the cycle number. Green is the cathode pristine, anode pristine, or CPAP. Orange is the cathode lasered, anode lasered. So this is benchmark in the pristine, and then the lasered channel in orange. And we can see at 6C for this thick electrode. Now, because it's so thick, we still didn't expect, obviously full lithiation or full utilization of the material, but we did see a substantial improvement in how much capacity we can get into the electrode in about 10 minutes. In fact, that improvement that we've observed through multiple repeat tests was on the order of about 100%. So about 40 milliamp hours per gram to about 80 milliamp hours per gram. And the life of the cell also is extended. So even at the C/2 at 50 and 100 cycles or so, or that looks like about 30, the capacity of the laser ablated channel is higher for C/2, and that's expected that the non-ablated electrodes incur very severe lithium plating. Now, we still expect that the ablated electrodes will incur lithium plating, that we're still working on quantifying, but you can see the capacity maintained at C/2 is much greater. So we expect the plating here is much more severe than here. And then if we look at the voltage cutoff, so this is the length of time that we can achieve the constant current step of 6C, we have an increase of about 45% or so, going from a constant current achieved for about 17 seconds to a constant current achieved for almost 30 seconds in these straight channel laser ablated electrodes. And so part of this project for the DOE's Advanced Manufacturing Office is also looking at the feasibility of scaling this process up. So we're currently at the benchtop laser ablation and looking at kind of more fundamental questions at this level, but in parallel, we're also working on scaling this up to a roll-to-roll process. We'll be getting a 300-watt laser, very, very powerful laser, installed at UNREL. We'll be installing this on a roll-to-roll laser processing line here, and we'll, in partnership with a company, we'll be taking full rolls of electrodes, passing this through the laser ablation, and producing a full roll of laser ablated electrodes that the company will then build into about 20 10-amp-hour prismatic cells for feasibility testing at scale. So the purpose of this is to demonstrate it at the pilot scale, and in addition to conducting electrochemical analysis, we'll be conducting an economic analysis of this process as well, of energy use, loss of material, cost of equipment, and whatnot, to determine how much of an economic impact this technology will have on the batteries. And our aim is to process about 10 meters per minute of laser ablated roll-to-roll electrode. And just to let everybody know, we're also looking at other channel dimensions like cylindrical channels spaced differently, and differently shaped channels that we're also exploring. Because we have to consider the scaling up to pilot scale in this project, the complexity of channels, we're not necessarily looking at best performance, but rather also thinking about technological feasibility of scaling up complex patterns. So some patterns some patterns that are expected to give the best behavior performance may not go forward to actual scale up. So in summary, fast charging of high energy density thick electrodes is severely limited by transport limitations and lithium concentration gradients. We get severe polarization in electrodes at high rates due to high current densities near a separator, favorable conditions for lithium plating. Reducing the tortuosity of electrodes can mitigate gradients in lithium concentration and current density and increase the fast charging capability. Strategic laser ablating channels into electrodes can reduce that tortuosity and increase rate capability. And we have ongoing work to demonstrate the feasibility of scaling up laser ablation to pilot lines. So I'd like to thank my colleagues, Bertrand, Donna, Francois, and Nathan for conducting most of the laser ablation work I showed today, and Changwan and Sam Gillard from the AMO and BTO for financially supporting this work. So with that, I'll take questions.
Thank you very much, Donal, for a very, very nice, very interesting concept. You present today. Very, very exciting. I had a question regarding the scaling up of this process, but I think someone else asked the same question in the chat, but you also answered partially this. You answered already this in your presentation, but Fernando, maybe you can go ahead with the questions?
Absolutely, yeah. Let's move on with that. Here we have a question by Avos Shodiev, who says, I am curious, what is the porosity change inside the electrode after laser ablation?
I don't have that figure on hand. If I were to make an estimate, I'd probably guess around, let's see, I guess around 50 to 60% of our current laser bladed, but it's very dependent on the actual pattern that we choose. So, but I guess about 50 to 60%.
Perfect, thank you.
Okay.
Also,
I think that there is a, sorry, Fernando, there is a question that was answered by Theo himself. So I think we need to read it.
Yeah, wait, let's maybe continue with the one of Avos before, because I think maybe it's connected with this. Okay. Then he says, maybe 10% sacrifice under a low C rate can be avoided by just changing pore size distribution, keeping the porosity constant at the same time. Do you think it can be done by laser ablation techniques?
Changing the pore size distribution. Yeah, that's a good point. So in other words, improving porosity in the channels, for example, and reducing porosity in the dense material, that could be another parameter that we look at. I expect, yes, that would very likely to lead to improvement if we optimize both porosity and of the active material, the dense active material, and the channels. I expect that would lead to improvement. That's for us. That's a parameter, a variable that's a bit beyond our scope, but that's a good idea. Yeah.
Okay, so now maybe we can check the question by Theo. I will resend the question myself here so we can show it. No, we cannot. I cannot.
Okay, I can do for you if you want.
Yeah. Wait.
So
there it
yes,
is. Oh, yeah,
it's done.
So yeah, Theo says, could you please comment on the feasibility of laser ablation in these industries? Do you think that the addition of this extra step plus extra capital cost plus loss of materials could be counterbalanced by the better performance of such electrodes? Also, wait a bit. He also adds, I guess that I had to wait for the end of your talk. You already said that you are working on this, but do you have an idea of the economic feasibility of such approach?
That is going to be part of our study. We are working in very close partnership with a company that have a pilot line in Michigan, and I've made a back of the envelope calculation on the cost it'll add. I estimated about 15 to 20% to a battery, but I acknowledge that I'm kind of ignorant to the costs at scale. Right? I don't know the cost of electricity that the company uses. I also don't know the production rate of the company, and the cost will be very sensitive to the cost what the company pay for electricity and their throughput, because the technology itself will cost money. It's not, these high-powered lasers are not cheap. Easily can go into the millions, and but if the company has a very high throughput, then the cost of technology, might be a small fraction of the total cost of the plant. At the end of this project, in about 2 years from now, as we fully demonstrate this, we do intend to conclude the project with best estimate economic analysis of all those parameters of electricity cost, capital cost, and make an estimate of how much it would add to the cost of the battery. My very amateur back of the envelope was about 15 to 20%, but that could be less.
Perfect. So here we can take another question from Pranab Karanth. I hope I pronounced that well. Here the question is, could you comment on the porosity of these electrodes, considering the volumes of the channels created in comparison to the porosity of state-of-the-art NMC graphite electrodes?
Yeah, I think typically state-of-the-art electrodes have a porosity of about 25% or so, 25 to 30%. We would, with introducing these channels, we'd increase the porosity, I guess, to about 50 to 60% for thick electrodes. So that's kind of the range, and there could be other benefits as well of the channels. for mass production. So that the loss of active material may benefit in not only rate capabilities, but other ways as well, such as wetting, which is a challenge for industry.
Donald, can you comment about the mechanical properties of the electrodes? I mean, with the creation of these channels.
Yeah, they're still very good. We've conducted bending tests, and we haven't done tensile tests and stuff like that. But I think the tensile is mostly governed by the current collector, so they're still very robust. And I don't see any issues with reduced mechanical properties on the production line. Mm-hmm. Now, even if there were the direction of the straight channels would also determine mechanical properties. If we do them in a machine or transverse direction, one will be better than the other.
Mm-hmm. So here we have another question. Do cells made with the channels require extra electrolyte and solvent to fill the extra void space?
They will require extra electrolyte, yeah.
Okay, nice. Imagine that you take your electrodes and then you do calendaring on top of that. So that board channels will collapse, or what is going to happen in this case?
Yeah, we've been doing that. So far we've been doing it on pre-calendared electrodes. Mm-hmm. But that's a good point. That's another variable for optimization. That is it better to do this before or after calendaring? That's also a technical question. Is it easier to do it before or after calendaring? So I mean, you'd expect that after calendaring, the channels will close in on themselves. There could be benefits to that. But for this project, given our access to materials, we're just sticking with pre-calendared electrodes. It's another interesting variable. I agree, but we probably won't get into that.
Okay, great. Fernando, do you have more questions?
No, I think we have covered them all. Yes.
Okay.
Here we just received a new one. Let's see. So Anthony Bambaqueros asks, do you expect the chemistry could change locally at the electrodes due to the laser?
Great question. That's something I didn't include in this talk, but yes, absolutely. Now, for the graphite, we don't think so. The graphite will probably be burned and bladed out of its presence, but we have observed some structural change of the NMC. With local high temperatures, it probably sheds some oxygens, right? So we might get a higher concentration of metals close to the surface. But there are ways that we can mitigate that, and we're looking into that as well. Ways that we can remove material with minimal heat load, and that might involve pulsing in one area, pulsing in another area, returning to that area, pulsing there. This is a femtosecond laser, so we're talking about pulses of 10 to the minus 15 seconds. And heat dissipation can be very well controlled with such accuracy of pulses. So that's a great question. There will be damage under some operating conditions, and there are opportunities we think to minimize that damage through strategic laser ablation strategies.
Great, Donald. Okay, there are more questions, no? I think.
No.
Okay, it's fine. Okay, Donald, many thanks for having accepted the invitation, for your great talk. I mean, great discussions here, and well, it's a great honor to hosting you here today. Many thanks once again. And well, I'm very much looking to continue our collaborations and so on. I mean, I see plenty of complementarities between the experimental work, the characterization, and also digitalization, right? And well, it's a real pleasure to interact with you. Many thanks again.
Yeah.